Okay. So how many participants do we have now? Santosh, can you put me a spotlight? Thank you. So we're at 141. I'll just wait for 3 more minutes and start at 10:05. In the meantime, uh, I did notice some questions in the Google, in the form that was circulated to you. So let me try to answer them. So one is from Vinisha Kalwani. What is the reason for the absorption of certain radiation while visible radiation process? Is something to do with the wavelengths? That is right. I think I had briefly mentioned this yesterday as well. That the basic absorption process is related to quantum mechanical transitions. We go from one state to another state. Another way that you can absorb radiation, and we'll see briefly about that in the brainstorming session. For example, you have a continuous distribution of energy levels, and it's like a continuous absorption. But what more importantly happens, say, for example, with the gamma rays and X rays, is the photons scatter with the atmospheric photons, and during this scattering process, it gets absorbed. So it is directly related to the wavelength, but the way it happens, whether it's a single quantum mechanical transition or it's a scattering process or a continuum process, that is different. Yeah, I don't know if the person who asked is there. Then Shantan Chakraborty asks why absorption is different for different parts of the spectrum in the atmosphere. Again, I briefly just responded to it. It depends. The absorption scattering cross section is depends on the frequency of the wavelength, that is of the frequency of the radiation that is being scattered or that is being absorbed. So that is one of the reasons. Okay. Mohammad Rehan had a question, but this is not related to what I am teaching. So your question is why variable stars, intensity fluctuate. I guess what you're trying to ask is, why do some stars which have fluctuations in their intensity pattern? And that has to do with the stellar physics. I don't know if stellar physics has been taught to you in this course. If so, you'll hear more about it. But there are mostly thermal instabilities and radiation-driven instabilities in the upper envelopes of the stars that causes some hydrodynamical modes to develop, and there are oscillations in the stars. And this is the surface area of the star is oscillating. It also gives out results in variations of the intensity pattern that you observe. But this is related to the stellar physics, nothing to do with radiative transfer. Okay, I responded to Spandan's questions yesterday regarding S and S prime. Okay, Subrata is Shubrata Sarangi, and your question is, how do you justify that the radiation received from the surface of a star is a black body radiation? Well, the best way to justify it is just take the spectrum and fit the spectrum with the black body function and see what you get. The question is it truly a black body radiation field? It's not often true that the telespectrum are completely and absolutely black body. I'll give you one example of what is of a astrophysical spectrum that is truly black body. But the stellar radiations are very close to black body radiations. We often have gray body spectrum from some of the situations. But the best way to do it is experiment. Yes, Shubhrata, please unmute.
Yeah, thank you for this answer. But there are two questions. One is are there any standard processes, known processes which are known to make this radiation from this stellar surface close to a blackbody radiation? I mean,
Yes. So if the radiation is coming from an optically thick region, it
right.
naturally goes towards the black body spectrum. And I will discuss black body today later in the lecture. So some of these concepts will
Okay, okay,
be better discussed, or maybe we can have a discussion later on this. But
okay, fine.
as I will show you that just using the basic formalism of data transfer, the intensity distribution function tends to the black body function at regions where it's highly optically thick. So in the stellar surface is optically thick part surrounded by optically thin atmosphere. So the radiation
Right.
coming from the optically thick part is naturally black body. That's from the theoretical
Okay.
point of view.
All right. Well, yeah, that's what I wanted. But if we
Oh,
see some graphs, some figures, it will be
hmm.
nice. Yeah.
Yes, yes,
Yeah.
yes, yes. Okay.
Sure, sure. Okay.
Okay, I got a very interesting question. Oh, what happened? Oh, sorry. From Hariharan, let me see if the person is there. Hariharan, yes. I guess this is the person who asked me. Hariharan Ramasubramaniam is online. So the question was, why do radiative processes, as if explained, not consist of refraction, reflection, or even diffraction? I joined the lecture a bit late, sir, but okay, that's a long comment. But I think the basic question that is asked is all of this that I was talking about yesterday about the radiation or intensity traveling on a line. How do we calculate the intensity distribution and variations? Where is refraction, reflection, or even diffraction involved in this? Very interesting question, and very true that radiative transfer processes will have to consider all of these things. But that depends on a particular situation. What I am telling you is the basic formalism. Of course, you can have a ray of light that goes and reflects from somewhere. Uh, to better study this, I'll actually point you to a book that we had studied long back during our masters and bachelors. It's Principles of Optics by Born and Wolf, Max Born and Emil Wolf. A fantastic book. It's a bit old book, and I'm not have not kept updated with that part of the subject, so I'm not sure whether any new text has come up with a better development of the theory. But this what this book does from the optics point of view is starts off from the basic Maxwell's equation and derives the basic principles of optics, which includes both reflection, refraction, everything. So have a look at that book, and that gives you a more better modified answer. For example, if you have a different refractive index, how will the ray of light travel? What would be its trajectory if you have a say differentially varying refractive index, etc. All these are nice problems actually, and they should be accounted for. In our astrophysical scenarios, we will be considering very simple cases and not going to the such details. Of course, if you have a ray of light going and entering the sun, you might have that light to be bent, but that is not that we that is something that we not consider in the kind of formalism that we do. There was a raised hand. Dibakar Datta, please unmute yourself and ask if you want to add to the discussion. Dibakar Datta?
Sir,
Yes.
yeah, sir, my question is, will you be discussing about both ionization in your lecture, any of the lecture?
Dibakar, you are not audible. Can you either make yourself louder or type the question in the chat?
Sir, I have typed it in the chat box. I have typed
Yes,
it in the chat box.
yes, yes. But it's better that you type in the chat box. Thank you. Okay, so I think that is it. And also, I just wanted to mention that even in astrophysical scenarios, we do have to consider reflection. I'll maybe give you one example right at the end. What happens is this occurs in the vicinity of accretion disks in near black holes. So, for example, as I was giving the example in the last lecture, you have the accretion disk that is giving you photons of radiation due to a black body distribution in the thermal plasma in the accretion disk. Now those photons goes and interacts with the hot electron distribution surrounding the accretion disk, and they are Compton scattered. So the Compton scattering then results in a different sort of set of photons. So the photons are upscattered. So they can either leave the system or they can come back to the accretion disk. So you can imagine, so if this is the accretion disk, some photons go, maybe I will just go to the last slide. I'm already sharing my slide. I'll go to the last slide of this entire lecture series, and this is what I meant. So the accretion disk, some photons are going and interacting with this hot electron cloud. Some of this hot upscattered photons will then just leave the system and go. But some of them will come back to the accretion disk. And once they come back to the accretion disk, they'll be reflected by the accretion disk and then go back. So then we'll have a reflected spectrum. And there are, of course, if this radiation or the physical processes that gives rise to the radiation is varying with time, there is a finite light travel time involved from this point to here and this radiation. So there's always some difference in the time of arrival of the photons that are coming from the scattering region and the reflected spectrum. And we can infer the distance from this by understanding the time delay. So yes, reflection is considered in while modeling actual astrophysical scenarios as well. Just wanted to highlight. Okay, so Dibakar, your question is, will you be discussing Bose ionization in your lecture? I'm not sure what exactly you mean by Bose ionization, but I will not be discussing Bose ionization then at my lecture. Keshav Agarwal, you are asking what are some of the ways of how solar corona can be studied in terms of radiative processes. This you better ask during the lectures in the solar in the solar lectures. I think there will be some few set of lectures in the solar domain, so you can ask them there. Okay, so I guess I'll start now. We're already a bit late, so welcome everybody. We have near 200 participants now. I've also finished my morning coffee. So in the last lecture, we saw how to build up some of the basics of radiative transfer processes. Not the processes, the basics of the fundamentals of the mathematical foundation of radiative transfer. We learned about the radiative transfer equation, the fundamental equation we use to solve for the radiative transfer, or understand the variation of intensity along a given ray. We learned about the definitions of emission coefficients and absorption coefficients. Okay. Today, and we also learned about the solution of the radiative transfer equation and what that solution implies at different limits. For example, if it's a purely absorbing system, the solution implies that the radiation gets attenuated or decreases exponentially. And if it's optically thick solution, then, for example, which means that the optical depth is very high or the radiation is coming from a region that has very high optical depth. In that case, the intensity along that ray just simply tends to the source function. So today we will jump into a different topic, not a different topic, but a slightly different flavor of the topic and see how it is connected to the definitions that we discussed last time. So I'm pretty sure all of you, since you are here from third year bachelor and onwards, have gone through this concept of blackbody radiation from different kind of sources, from your kinetic theory of gases, from your statistical mechanics, etc., and thermodynamics. So I will not deal with what is the definition of blackbody and how you can infer some properties of the blackbody. I will ask participants to please mute yourself. And also one other request is, if you have your Zoom name something to set to something different from your actual name, please reset or rename yourself to your actual name by which you have registered for the courses of the school, so that it's easier to identify people. Just for example, I saw someone with the name Carry Live Again. I'm sure it means nice, but it will be easier for us to address you if you just use your actual name. Thank you. Okay. So I can see there are some raised hands, but I'll keep typing the questions or keep your hands raised. I'll come back to the questions a bit later once I have gone through a bit of my lecture. Okay. So what I'll be talking about is how is the basic emission processes or the concept of black body radiation related to the definitions that we have introduced in the last few lectures. Definitions being the intensity distribution and how it is related to the radiative transfer equation. So, firstly, the basic definition of a black body. Black body radiation, as we have all learned how it is derived from early Planck's system, is you have a box that is enclosing the radiation, and the radiation is in thermal equilibrium with the box. And if a box is at finite temperature, the radiation is not is interacting with the box, and then nothing is changing. It's all steady state. So in such a situation, the radiation is termed to be a black body radiation field. So essentially, in most simpler physical concepts, the radiation is in thermal equilibrium with itself and the container. So in this case, we'll define that the intensity of a ray that is passing through a black body radiation field is B nu T. This is just definition for now. And I'll tell you what is the significance of this function called B nu T. So the intensity of a black body radiation field is B nu T, or I nu equals to B nu T. Note that. Now, just from the basic equations of radiative transfer, if an object is in thermal equilibrium, then the black body radiation field, or B nu, or the intensity of the black body radiation field is nothing but its source function. How did I get it? Go back to this equation. I just said that one of the basic assumptions of black body radiation field is it is not changing with time. It is in steady state and in equilibrium with the thermal system. In that case, if you just take the ray of light that is passing through the radiation field and also entering the system, then d I nu d tau is 0 because the intensity is not changing. So that means the intensity along that ray that is passing through the black body radiation field and also the source function and also the material all is in thermal equilibrium. So the intensity is not changing with optical depth. So I nu equals to S. Again, do note that I nu equals to S nu also appears when you have optical depth tending to infinity, or when you are in a region which is at high optical depth, which essentially implies that whatever radiation that is incoming is completely lost, and the source function is just an accumulation of the emission that is happening locally as well as the absorption process. So from this concept, di nu theta equals 0, we get that for a black body radiation field, or equivalently, in a region where it is optically thick and in a thermal region, S nu equals to B nu T. So in an optically thick region, your intensity is S nu. But if the optically thick region also corresponds to a thermal distribution of if the system is in thermal equilibrium with a finite temperature, then that becomes a black body distribution. Now, so this and this gives you the fact that S nu equals to B nu, or I nu equals to B nu T. Good. Now that we know that the source function is equals to the black body radiation distribution, then immediately we get one nice relation, which is the Kirchhoff's law. As you remember, the source function is the ratio of the emission coefficient to the absorption coefficient, which is J nu by alpha nu. Using this, what we immediately see, since for a black body system, the source function is equal to the black body radiation intensity field, or B nu, the black body function B nu, which it implies that for the thermal system, the amount of radiation emitted and absorbed is in equilibrium. So the emission coefficient is equals to the amount of radiation that is actually taken away from the black body intensity distribution by the thermal system. So this is nothing but the fact that the radiation level, no net radiation is added to the ray or subtracted from the ray. So that is why J nu equals to alpha nu B nu. And I have just stated this law here, which is the Stefan's law. This is not related to the black body, but I'll show you how this is how you can derive the B nu T from using this relation here. So this is the Stefan's law, which means that if you have for a black body radiation field, the energy density is proportional to fourth power of temperature with the radiation constant here. I have outlined the derivation here. You can do it from the first law of thermodynamics. I will not go into the details. I'm sorry, I have not uploaded my slides, but I will send the PDF of till the second lecture today to Santosh. We'll upload it to the website, so you can look at this in detail there. I'll not go into the details, but this is how you can. This is what I've sketched the derivation here. But taking the fact that we have the Stefan's law, which implies that the energy density of the radiation field is proportional to the fourth power of temperature. Now we can use some of the basic principles we've also already derived earlier and relate it to and use it to find the black body distribution function or the black body intensity function. We know that first of all, the black body radiation field is isotropic. So I nu is equals to the capital J nu. Capital J nu is the solid angle averaged intensity radiation field, but it's same since there is no angular dependence. J nu is equals to I nu is equals to V nu T. This is again just from the definition and the fact that it's isotropic. So what we do now is the fact that we are so UT or U is the total energy density, that is frequency integrate. So if you just integrate the black body, I have not showed you what the black body function is. I'll come to it in the next slide. But this is just a nice outcome of the fact that you have for this radiation field, the energy density is proportional to the fourth power of temperature. You get the Stefan's law in a different form, which is what we are more used to. So if you integrate over the black body over the frequency form for the black body function, you get something like this, which is 4 pi by c Bt, which is the frequency. Bt is a frequency integrated black body function. So Bt is sorry. So this is just equating this here. Bt or the black body as a function of temperature is Ac by 4 pi t to the power 4 after this integration. But do remember what we discussed while trying to understand the inverse squared law is the flux at the surface at a given surface of that uniform sphere that had a constant intensity is pi times p. Now we can always take any arbitrary sphere and find the flux at that point. And so the flux due to the black body radiation field is at a given surface that is emitting that is at thermal equilibrium, for example, and in equilibrium with the ambient radiation field, is sigma t to the power 4. This is the flux of the luminosity essentially is sigma t to the power 4. So this is the more familiar form of Stefan's law that you're used to, and this was derived using this energy density argument of the Stefan's law. So both are Stefan's law. This is the flux form of Stefan's law, and this is the total energy density form of the Stefan's law. Okay, so but what essentially we learned from this is the fact that the black body, the frequency integrated black body distribution function, is a function of temperature of the system, and that is also related to the fourth power of the temperature. Okay, now we'll go into some of the more formula-based applications of black body. So I will not go into the detailed derivation of the black body radiation field. That is not that will again take a whole lecture, and we don't have time for that. This is just introducing you to some of the concepts. So to get the full derivation, I have to use the Bose-Einstein statistics. In one of the ways of deriving it, you can have many different ways of deriving it. So essentially, you have to calculate the full phase volume and then integrate over the phase volume using the fact that you have a photon population using the Bose-Einstein statistics. After all that, generally, you'll find that the energy density is given in this, represented in this form, which is 2 nu cube by c cube, and the denominator exponential h nu by kt minus 1. It's a very well known and often seen form of the blackbody radiation field. Now, this is something that we are used to from the point of view of statistical mechanics or thermodynamics. What I wanted to relate to was how this formula that we have here is related to the intensity, or the intensity function that we use in our radiative transfer process. Because if you remember, to calculate the amount of radiation that is passing through a ray, we will not be using this, but we will be using this I nu, or the B nu function. Now, in the earlier part of the lecture yesterday, I had showed that the energy density as a function of the solid angle is equals to I nu by C. And for the black body distribution, I nu is the same as a B nu. So the intensity of a black body radiation field is thus 2h nu cube by C square exponential h nu by kt minus 1. Okay, so it's just C times U omega. So this is the black body function that we use. And the black body function, it relates the intensity of a black body radiation field to the frequency and the temperature. Now we can have several limits depending on which frequency range we are interested in, as well as and its relation to temperature. If h nu is much less than kt, then we can expand this terms, expand the denominator, and we get b nu t is linear with temperature and proportional to nu square. Okay, so this is called the Rayleigh-Jeans limit, and this is mostly used for cases when the part of the radiation that you're looking at is of lower energies compared to the temperature of the system. A typical such application is, for example, in radio astronomy, where the wavelengths are large, so that means the frequencies are small, and the h nu by kt, or the temperatures of the system that you're trying to model, is larger than the h nu. So this is often used, and in many of these cases, what we do is ascribe a brightness temperature to the observed radiation field. So, for example, even if it is not a thermal system, what we do is we take the radiation field and then divide by 2 nu square, divide by this coefficient in front of it to get an effective temperature. Now, if the object that is emitting this radiation field is actually thermal in nature, the calculated temperature that we get, or the brightness temperature, will relate to the thermal component of the temperature of the emitting region. So that will truly represent a proper temperature. However, if the object that is emitting the radiation is actually not a thermal system, if it's, for example, a non-thermal radiation field, there are several examples of non-thermal radiation, for example, a Compton process or synchrotron process, etc. In that case, we can still ascribe a brightness temperature, but the temperature has no physical meaning. It is just an empirical quantity to parameterize or classify that particular object. So, for example, the brightness temperature of the interstellar medium, for example, can be something like 10^4, 10^5, which is fine, because in many of the gases that we actually observe from the interstellar medium are at such temperatures because it is in equilibrium with the photoionizing medium, with the photoionization, background photoionization. However, we often see radio emissions from, say, relativistic jets from active galactic nuclei. We all saw this nice image, for example, of the center of our galaxy recently from EHT, or earlier, a few years earlier, from M87. And this galaxies and these black holes can give out relativistic particles that come out from near the black holes, not exactly from the black hole, but near the surface of the black holes. When we observe such relativistic particles, they emit radiation due to several processes. Synchrotron, for example, I'll come to synchrotron process in the next lecture. But when they emit this radiation, those particles are not in thermal equilibrium. So when we observe the brightness temperature or observe the intensity from these and calculate the brightness temperature, they can be orders of magnitude higher. So they can be of values of say 10.9, 10.10. And even sometimes when the jet is pointing towards you due to relativistic boosting of the radiation field, just a special relativistic effect, it can go up to 10.12 or 10.30. Such high temperatures are not expected. So it clearly shows that these are non-thermal in origin. The reason why I'm saying so much about it is because many a times when you're going through the literature in astronomy, you'll come across this term of brightness temperature. But do not mistake brightness temperature to be a thermal description of the object. It's a purely empirical description. And the way we often calculate brightness temperature is using the Rayleigh-Jeans form of the Blackbody function. Okay. The other limiting case of the Blackbody function is the Wien distribution. When the frequency that we're observing of the photons that are coming towards us are highly energetic compared to the temperature of the system. So if h nu by kT is much larger than 1, again, we can expand these terms here. And what we get is a power law in frequency up to a certain point, and then suddenly, as the h nu becomes larger than kT, or the frequency increases larger than the temperature, equivalent temperature, you have an exponential cutoff. So this kind of systems, what they have is a power law with a cutoff in their tail, and that is the Wien limit. And we can see the imprint of this in spectra of X-ray in X-ray astronomy, where, for example, you have highly, as I was giving the earlier example of photons from the accretion disk going and interacting with a hot electron cloud, and they're getting Compton upscattered. All of this will always follow with the exponential cutoff. So you have if the photons are coming from the accretion disk, for example, forget the Compton process, because the Compton process introduces other complications. But if you just consider the photons from the accretion disk, as you go to higher frequencies, and we do have to go to higher frequencies, you have a power law and then a certain fall off, and that is called the Wien limit. So if you plot, besides the Rayleigh-Jeans and Wiens, okay, so this is the plot of the Blackbody function represented in terms of the frequency. And as you can see, for different temperatures, the curves do not intersect. They envelop each other, because each of these curves at different temperatures represent the integral of this will represent the total energy density. And if your system has a different temperature, the energy density is higher. So the curves progressively keep going higher over one another. And the peak of the curve can be found by just taking the derivative of the Blackbody function, and it is related to the temperature in this way. So h nu max is 2.82 kT. So h nu max is this particular point. And this is called the Wien's displacement law. So this gives you an approximate estimate of the temperature of the system. So if you plot the function, if you identify the nu max, you can get an approximate estimate of the temperature of the system. And one of the most well-known Blackbody distribution is actually the cosmic microwave background. This is the spectrum from one of the early missions of that detected CMB, is early space missions from Kobe. And as you can see, it fits in beautifully with very small deviations or errors. Okay, so in the next, I will slightly shift gears and move to something else. And before doing that, let me see if I can take any questions. So if you have any questions, please raise your hand. I can take a couple of questions. I can see some of the questions. So Dibakar Datta, Boltzmann-Saha equation. I will not be discussing the Saha ionization equation. Sorry, I understand what you mean now. No, the Saha ionization equation maybe will be covered by somebody else who works on the stellar, who will be discussing the stellar atmospheres. Sir, does this energy density in the Stefan's law account for emission as well as absorption? Energy density uh, well, this is just a total energy density in the radiation field. This is not related to the emission or absorption. So the total energy density in a blackbody radiation field is given by that. How it is derived, you have to go to the details of the statistical physics and Bose-Einstein statistics, which I will not go into the details now because that will open up a long chain of discussion. Sanjana asks, any relation between de Broglie wave and the acceleration of the particle? Not relevant for this discussion. Okay, there's a one interesting question. Can you please repeat the importance of non-thermal? Where did it go? Important non-thermal process. Why is it empirical? Okay, so what I meant by importance of non-thermal process was when you I let me go to the particular slide. Okay, non-thermal processes are not empirical. What I was saying was the temperature that you find for a non-thermal process, that is empirical. So what we do is what we are observing from Earth by carrying out this radio transfer equations is identifying this B nu or identify the intensity that we get. The intensity that we get is not related to the blackbody radiation field if it is coming from a non-thermal radiating source. So I nu is not equals to B nu T, but we still use this as approximate or this empirical relation that relates the intensity to the temperature. If it is coming from a true black body, then that represents the temperature of the black body. If it is not a black body radiation, then whatever the T that we calculate by dividing the intensity with 2 nu c square kb and then multiplied by 2 nu square kb and multiplied by c square is an empirical quantity. So it is not that the non-thermal process is empirical, but the temperature that we infer about the non-thermal process using this relation or I nu equals to 2 nu c square by kT is empirical. Okay, now I'll just take one last question. Shlok Shah, can you unmute yourself and ask the question?
Hello, sir. Am I audible?
Yes.
Sir, in the beginning, you talked about reflection spectrum. So, how do we differentiate between reflection spectrum and normal spectrum?
When you are reflecting the spectrum, it undergoes some changes in the spectral properties. For example, the incoming spectrum has a distribution with frequency. Different photons will be reflected in a different way. So there is a change in the spectrum. Also, it's not just simply a change in the spectrum. There's a time delay between the two spectra. So, for example, the true spectrum that is coming towards you consists of high energy photons. But once it is reflected or reprocessed, then that spectrum becomes slightly lower in energy because it loses a bit of the energy. So that becomes a bit softer. So there is a lag in the frequency and also lag in the timing. So there's a change in the spectrum depending on the reflection process. What exactly is the change in the spectrum? That depends on the particular process of the reflection. Okay, so I think I will just pause now and go to the next few slides and see how much I can cover now. And if you have any questions, you can keep writing on the chat box or on the Google form. I'll try my best to address the questions in the chat box, but if I can't, then put them on the Google form. Okay, so next is we'll be discussing some things related to Einstein coefficients and how they're related to the radiative transfer processes. So as I said, the emission and absorption phenomena is essentially from a quantum mechanical perspective is nothing but transition between two levels. Okay. And this is true. Even if you go to go to a classical system, you don't have discrete energy states, or you don't have discrete emission at certain frequencies, and you have a continuum emission. This fundamental property is still true. What happens in that case is the energy levels are not very distinct or discrete, and you have a wide variations in the energy levels. I will not go. I think I'm not going into the. I don't recall that I'm including this, but there's a nice discussion of this in the Rebecca Enlightenment, where we generalize the two state transitions to a continuous distribution of energy levels, energy systems. All right. So, but before that, let's just try to understand what this two state means. So, suffix A, I see you have raised your hand. Please lower the hand and write the question on the chat box, or wait till I pause again at the end of the lecture. Thank you. So, there are a few basic assumptions, and this comes from the time of Einstein, which got him the Nobel as well. So, we have a two-state system, state one and state two, and the system can transition from state 1 to state 2 and transition back from state 2 to state 1. If it transitions from state 2 to the higher energy state to low energy state, of course it will give out a photon. So the question is, at what situations will the photon be given out, and what is the rate at which it is doing so? That defines our intensity of emission from this particular region. So first is a spontaneous emission. So this is the probability of transitions. And first is a spontaneous emission. So the system is in state one, state two. It can spontaneously decay into state one. There's a finite probability for that, and that is termed as that probability is termed as A21. Now there can be absorption. So absorption is when you have an incoming radiation field that comes and interacts with the system at the lower state, and the system then it transitions to the upper state. So, in a more formal way of saying this, if J nu is the um, solid angled average emission intensity field from this region, then what we usually define is not exactly J nu, but something called the J bar, which is integrated over the small profile function. So profile function is we assume that this level 1 has a finite frequency, but as we all know that there is nothing finite because there is a certain level of uncertainty involved in the quantum mechanical systems. So that is represented by this profile function phi nu, where you have a small variation of the frequency. And what we say is that this intensity or this J bar is an integral over this small frequency range, which is essentially a delta function, but represented by a Lorentzian function usually. So what we say is that the absorption process is proportional to this coefficient B12, and it is also proportional to the intensity of the incident radiation field. So you have an incident radiation field, J bar, and that is of course depends on the frequency. So the incident radiation field can have a wide range of frequencies, but it will only pick out the frequency at that particular nu and spread over the profile function. So the absorption is, so the takeaway point is the absorption process is, or the rate of absorption is proportional to this coefficient B12 and then J bar. J bar is the incident radiation field. Now, similar to absorption, we can have a stimulated emission. Whereas if you have an incident radiation field again of J bar, and this again is related to the frequency at which this transmission is taking place. The photon can be emitted or can be stimulated to to emit, or the atom can be stimulated to make a transition from state 2 to state 1. This is so far an assumption, and this assumption is what gives us the blackbody spectrum as we'll see now. So the nature of the transitions are: one, a spontaneous transition from state 2 to state 1, an absorption process that depends on the incident radiation field, and an emission process that also depends on the incident radiation field. So stimulated emission, you can also think it of as negative absorption. Absorption means you have an incident radiation field that is J bar, and that a photon from that radiation field is absorbed by the system, and the system makes a transition. So that is an absorption. But in stimulated emission or negative absorption, the photon is sent back to the system with this at the same frequency with this following probability. Now, if the system is in thermodynamic equilibrium, then the total number of transitions, that is total amount of emission and absorption, will be same. If it is not giving out any net absorption or any net emission or not performing any net absorption. In that case, we just add all the emission processes and the absorption processes and equate them. Okay. So absorption is N1B1 to J bar, and emission is N2A21. And N2 is the number density of the particles and at the state 2, and N1 is the number density at the state 1. So once you equate all the emission being the spontaneous emission and the stimulated emission and the absorption process, we have a net expression of the incident radiation field, which is in thermodynamic equilibrium, which is in equilibrium with this particular system or the particular two-state system. By equilibrium means this particular two-state system is not contributing any net emission or not even taking out any net energy from the incident radiation field. So in this case, the incident radiation field is in equilibrium with this particular system. There's no net addition or subtraction that is going on. So this is related to these ratios of these coefficients and the ratios of these two states. Now these coefficients are called the Einstein coefficients. And if you, again, from thermodynamic equilibrium and again from basic statistical physics, we know that the states are the densities of the particles to be in state 1 and state 2 is related to the energy at that particular state. So this is given by G1, which is the degeneracy of each level. That is the total number of combinations by which that particular level can be prepared. So G1 exponential minus E by KT divided by G2 exponential minus E plus H nu by KT. So the state 1 is just the energy up to that particular state and divided by KT. And state 2 is the energy at that state plus an additional H nu, which is the transition between these two energy levels. Okay, so essentially the ratios of these two densities then becomes ratios of this degeneracies times exponential H nu by KT. Okay, and if you now put this in, you have a very familiar form, which is the J bar is A21 by B21, and this ratios of coefficients and exponential H nu by KT minus 1. And J bar, again, do remember that this is the intensity of the incident radiation field. So if we naturally compare this with the Blackbody radiation function, we immediately get some constraints on these coefficients. So as you can see, we immediately get two such relations. One is this will be 1 because in the Blackbody radiation function, there is nothing in front of the exponential. So G1B12 is equals to G2B21. And this thing on the numerator is then related to the coefficients in the Blackbody function, which is 2h nu cubed by c squared. So these are called the Einstein relations. What it says is if you can measure at least one of these transition probabilities by some other mechanisms, for example, laboratory experiments, then you can infer all the other two. So for example, if you can find the absorption coefficient, you can find the spontaneous emission coefficient and the stimulated emission coefficients. So this is a nice relation. Oh, I do talk about the total absorption, and I wanted to sort of go to this. Okay, maybe I'll try to speed up a bit. Okay, so far so good. Next, we'll talk about how we can relate the Einstein coefficients to the absorption coefficients and the emission coefficient that we have defined so far. So the emission coefficient in terms of the Einstein coefficient is nothing but this. So emission coefficient. So for this particular system, where sorry, if you can see my, yes, I hope you can see my cursor. So for this particular two-state system, where it is emitting a photon after it is transitioning from state 2 to state 1, and this is the spontaneous emission coefficient, A21. So I'll tell you why I'm not including stimulated emission in this particular system, in this particular relation soon. But let us just talk about the emission coefficient being the spontaneous coefficient for now. So A21 N2 and A21 phi nu gives you the probability of this transition to take place. And this H nu is the energy of this transition, and N2 gives you the total amount of energy and the number of atoms in that particular state per unit volume, and this divided by 4 pi. So this is nothing but the emission coefficient, which gives you the energy per unit solid angle. That's why we're dividing by 4 pi, because it can emit over any different regions per unit time. And phi to 1, 8 to 1 gives you the per unit time, because it's a transition probability. And phi nu gives you the per unit frequency as well. So this is nothing but the emission coefficient. Because if you remember what this phi nu means is phi nu, integral of the phi nu d nu is 1. So the phi nu gives you the distribution of the A21 coefficients as a function of frequency. So in terms of the dimensions, if you take this, then this is same as the definition of the emission coefficient. Okay, so this is how the emission coefficient is defined for two-level system in terms of the Einstein Einstein coefficient. Now let us look at the absorption process. So what we want to find out is the total amount of absorption taking place in a unit volume. Okay, so then what we have to do is, first of all, as we know, the absorption process is in terms of the Einstein coefficient is proportional to B12 times the solid angle average intensity distribution that is incident on the photon. So if your incident radiation field is I nu, then we integrate over the frequency and we integrate over the solid angle and divide by 4 pi. This multiplied by the total number of atoms at that particular energy state N1, and this and the amount of energy absorbed is proportional to H nu, because that energy would be taken out from the radiation field for the thing to make a transition. And this in a unit volume dV, and then in unit time dt. So the total energy absorbed in time dt by this unit volume dV is given by this expression. Again, what we are using is nothing but these are the standard definitions, but the fact that the absorption process itself is the probability of absorption is proportional to this Einstein coefficient B12 times the J bar, and J bar is the solid angle average incident intensity distribution. So this is the total energy absorbed per unit frequency per unit solid angle. Now you just take out the integrals over the frequency and solid angle is given by this. After some again, I'm running out of short on time, but after some rearrangement of the terms, you can find that the absorption coefficients alpha nu is related to the frequency in this and the Einstein coefficient in this way, which is h nu by 4 pi times the particle number density n1 and then p12. So this is the absorption coefficient for the atom to take away energy from the system and transition to level 2. But as I said, stimulated emission is also in a similar way treated as an absorption, but negative absorption, which is if you have the transition probability is proportional to the incident radiation field. Even in the absorption case, the transition probability is proportional to the incident radiation fields, which is B12 times this. But here in this case, energy is taken away from the incident radiation field. But in the stimulated emission, again, the transition probability is proportional to the incident radiation field, but radiation is added to the radiation field. So if you take an absorption coefficient, stimulated emission is nothing but is similar in terms of the mathematical formulation, but negative absorption. So that is how we treat it. We treat it as a negative absorption. And so this is the full expression of the absorption coefficient in terms of the Einstein coefficients and the degeneracies and the ratios of the level populations n2 by n. Sorry, someone was unmuted. So if it is in thermal equilibrium, so what you must note here is this up till this point, we have not assumed thermal equilibrium at any point. All we are doing is understanding that there is a two-level system and there's a finite probability of atoms to be in state 2 and state 1. And this is the absorption coefficient for that system. Now, if the system is in thermal equilibrium, then of course we can say that we can have an expression of what this ratio of the N2 and N1 would be. And this is nothing but exponential minus hν by kT, which I just showed in the slides, in the few slides back. So if it is in local thermal equilibrium or LTE, the absorption coefficient is related to the Einstein coefficient in this way. And if we know the energy density, if we know the number density, if we know the Einstein coefficient, we can immediately find what the absorption coefficient is of this particular system. The last thing I wanted to talk about, and before I go into moving charges and beaming, is what happens since we are talking about emission between two-level systems. We are talking about emission lines. What happens when you actually observe some emission line? Again, this is not exactly related to the emission coefficients and absorption coefficients, but these are concepts that you will naturally face once you start to study emission lines. So, as I said, the transition between two states occurs at a particular frequency, but that particular frequency is not exactly discrete or finite. There's always some uncertainty involved in it. So when you observe a line, it's not always at a small finite, exactly at that frequency, but there's a spread in frequency. And I wanted to briefly mention what are the different processes that contributes to this spread in the frequency. One is naturally comes from the quantum mechanical broadening, because there's a finite transition probability or a spontaneous decay rate. It's again related to the Einstein spontaneous transition rate. So this is usually modeled as a Lorentzian, and phi is, for example, the total width of the total profile function. As I was just talking about the phi nu, this gives you the profile function. So if it's exactly at that frequency, this will be a Dirac delta function. If you integrate over the phi nu d nu, you get exactly nu. But if it is not exactly a Dirac delta function, if it has some natural spread, then it can be well approximated by a Lorentzian function. And this is the Lorentzian function where gamma is the spontaneous decay rate. Now, next, suppose the atoms are moving around. Okay. Now, since the atoms, if it's a thermal system, so you will for any of these atoms, from the atoms at rest, it will still contribute some width due to the quantum mechanical broadening. But since if you have a thermal system with all the atoms moving around, because as from the kinetic theory of gas, are moving around at a finite temperature, the atom that is in motion, once it emits that radiation, it will be Doppler shifted once it reaches to the particular observer. So there is a natural width involved due to the Doppler shifts in the frequencies that are coming in. So this is related to the thermal broadening. Sorry, I can't seem to. So this is related to thermal broadening. So you just take the Doppler relation, and we know what will be the distribution function of this particle. So this is a thermal system, and the particles will follow a Maxwellian distribution. And so we know what this velocity distribution will look like. And for a given velocity, the Doppler shift in that particular of the frequency will be given by this. So if nu naught is the frequency at which the atom is actually making the transition at rest, the frequency that you will see will be shifted to nu, and that is related to the velocity in this way. So after some rearrangements, again, I don't have time. I have to go to finish the lecture by 11. you'll find that the probability distribution of this particular system, just taking the velocity distribution to be Maxwellian along a given direction, and since we are looking at the spectra by probing a line through this particular relation, we use the one-dimensional Maxwellian, not the full 3D Maxwellian to find this. You can naturally just convert the velocities in terms of the frequencies, and you get that the fact that you have a Gaussian distribution of the probability and distribution of the frequencies. Again, if you have a profile function, so what is the probability at which you'll get a particle with velocity v? That is given by this. And what is the probability that the particle with velocity v will be giving a frequency at a given will give emission at a given frequency omega? That is given by this. So this is a probability distribution function of the frequency. Again, it naturally gives you the width of the line profile. So due to thermal broadening, you have a Gaussian distribution of the lines. Okay, now this is also called pressure broadening or collisional broadening. What happens is if suppose the given particle is traveling and emitting this radiation. Okay, again, I will not give you the full sketch of the derivation because we're out of time. But it is there in the notes. You can just follow and ask me questions in the next lecture. But what happens is, as the particle, if it is emitting radiation, let's say it is giving out electromagnetic radiation at a particular frequency, then the phase will change if the particle collides with something. Okay. Now this process of collision is actually a Poissonian process. So if we just take the magnitude of the electric field that the particle is emitting, again, and take a Fourier why I'm taking the Fourier transform, this perhaps will become a bit more clearer when I talk about the electric field from moving charges and how we relate that to intensities. But let's say we take the electric field, and that is proportional. So the Fourier transform of the electric field, the square of the Fourier transform of the electric field is proportional to the spectrum of the radiation that we observe from this particle. So the electric field is given by this, and this e to the power I omega t is just a standard oscillation, and minus gamma t t by 2 is just a spontaneous decay time. Okay, so then then we have this random phase term here. This phase of this electromagnetic radiation can change due to collisions of the particles. If you take a Fourier transform of this, and the square of the Fourier transform is related to the intensity, or related to the spectrum of the particle, and spectrum is actually proportional to the intensity. Spectrum meaning the energy per unit frequency, and again, intensity is also per unit frequency. So after some brief mathematical calculations, you'll see that in such a system, but the phase of the particles are changing, and gamma is just a spontaneous transition again, the quantum mechanical broadening, but the phases of the particles are changing. You naturally get the fact that the Fourier transform of the electric field is proportional to a Lorentzian function, where the width of the Lorentzian or the width thickness of the Lorentzian is now proportional to gamma by 2 plus nu c, where nu c is the collision rate. So if there are no collisions, if it's a purely quantum mechanical broadening, it's a Lorentzian function with gamma by 2 of the width of the Lorentzian. But if the particles are interacting and changing in phase, then the width of the Lorentzian is gamma by 2 plus c. So essentially, we have two different natures of the profiles depending on what are the physical processes that is causing the broadening of these lines. One is thermal broadening, where it's the fact that the particles that are emitting are moving about and are at a finite temperature, and it is the Doppler shifts in this, and due to this motion that is giving rise to the broadening. And the other is the particles are colliding with one another. So depending on the collision rate, so collision rate will also depend on the density of the particles. If the density is very low, then the collision rates would be much smaller. So which of this broadening process dominates the spectrum depends on the physical process of the gas. For example, if the gas is very cold, then the Doppler broadening is very small, but the gas can still have broadening due to collisions. So cold gases are often dominated by collisional broadening, but hot gases by Doppler broadening. So if you see an actual profile, what you have is a convolution of contribution from both a Gaussian as well as a Lorentzian. Gaussian because of thermal broadening, and Lorentzian due to natural, well, the spontaneous quantum mechanical transition is called natural broadening, and the collision-based broadening is called collisional broadening. So a convolution of these two give you something called the void profile. I'm not sure whether you encounter this later on in your in summer school or the refresher course, but it is important to know that when we actually fit spectrum of extragalactic sources, it is mostly advised to use a void profile unless you are sure that one or the other mechanisms are dominating. Then we can just use either the Lorentzian or the Gaussian. So I will end here today. Unfortunately, I am personally short of time.